So in this short video, what we'll do is we'll take a look at what is the power of a backtest and how can we increase it. To understand this concept, the first thing which you have to understand is that the backtest is basically a hypothesis test, right? And therefore everything that we learned about hypothesis testing, I mean type 1 errors, type 2 errors, probability of type 1 error, probability of type 2, all that applies to backtesting as well. So what we are focusing on here is the power of this statistical test, a test which tries to test if a given VaR model is working the way it's intended to, okay? So the power in this case would be the ability to reject a false or an improper VaR model, okay? So that's how I would define power. How would you define the probability of that happening? Okay, the probability of that happening, by that I refer to the rejection of a false model. The probability of that happening, we say, is 1 minus beta, where beta is the probability of committing a type 2 error. Okay, so what is a type 2 error here? A type 2 error is an error in which you do not reject a bad model. So that's a type 2 error. Okay, now let's do this. Let's start off with writing down some nomenclature. So we are saying that we have a VaR model. Okay, let's assume that it's estimating the VaR at a certain confidence. Let's call it CV. The reason I am subscripting it with a V is because when you do a backtest, there are two confidence levels floating around, one for the VaR model, one for the backtest, and there is a set of two level of significances floating around, one for the VaR model and one for the backtest. So let's subscript them appropriately. So we are saying let there be a VaR model which is computing the VaR at a certain confidence. Typically speaking, we know this confidence is 99%, and let's say it's doing so over a horizon of 1 day, and you are trying to backtest this model using a confidence level of, let's say, 95%. Okay, so that's what I call CB. So analogous to these two confidence levels, let's write down the level of significances. So in this case it will be 1%, and in this case it will be 5%. Okay, now if you were to backtest this model, we know that we do it via this variable x, where x denotes the number of exceptions or exceedances to this computed VaR. Okay, if x is a random variable, then given this specification CV, and there's one more specification actually which I've missed out, and that is the length of the backtest window. Let's assume that I'm conducting this backtest by comparing the published VaR or estimated VaR of any given day against the actual PNL, and I'm doing so over a period which I refer to, a historical period, which I refer to as my backtest window. So let's say it's T days long, this backtest window. Okay, so if that's the case, then this X, which is the number of exceedances, would follow a binomial distribution with parameters which will be given as the number of trials would be T, and the probability of success, wherein we call an exceedance or the exception as a success, I would write it down as alpha V. Okay, because if the VaR model indeed is computing VaR at 99% confidence, then there is a 1% chance that your PNL can be worse than the VaR. Okay, and therefore we say the probability of the exceedance is alpha V. Okay, now if that were to be the case, what is the implication? The implication is that the expected value of this number of exceptions would be NP. So N here is T, and P here, the probability of success, is alpha V. So this is my expected number of exceptions. The variance of this number of exceptions would be NPQ. So here it would be alpha V times 1 minus alpha V. This is the P, this is the Q, and then you have N, which is T. Okay, so far so good. Now let's before we actually go ahead, let's just write down our rules of thumb here itself, okay? And let's try and in the remaining part of the video, try and substantiate it, okay? So the rules of thumb which I am looking for are to do with increasing the power of the backtest. So in a very layperson's language, let's increase the power of the backtest by giving this guy, the validation guy, more exceptions to play with. That's how you would phrase it in a very layperson's way. How would you give him more exceptions to play with? By increasing number of expected number of exceptions, okay? So how would you do that? You would do that by increasing alpha V. Commensurately, you can say this can be done by decreasing the level of confidence at which the VaR is estimated. This is number one. And or you can do it by increasing the length of the backtest window. Let's run this backtesting over a longer historical window. That's the second way I can do it, okay? Now, this was about the rules of thumb, okay? Now, let's try and see why this is the case. So, to understand that, let's do this. Let's consider two analysts, okay? There is an analyst A and there is another analyst B, okay? So let's say B really does adhere to what you tell him to do, and you are telling him to basically follow these two rules, and A does not listen to you, okay? So what A does is that he conducts a backtest, let's say over a 2-year historical window. If there are 250 trading days in that year, that means he is conducting it over a sample of 500 trials, okay? So that's the backtest window for A, and let's assume, hypothetically speaking, that he is using a VaR model whose level of significance is 2%, okay? Analyst B listens to what you are saying, and what he does is he doubles the backtest window. That means he runs it over a span of 4 years, which gives him 1000 trading days to play with. And the VaR model, which he's working with, let's say, is computing VaR at 97% confidence, which means 3% level of significance. Now, before we move ahead, let me ask this question. Is this under your control? Well, no. You are not allowed to, let's say, choose whatever level of significance that you would want to. But what we are proposing here is that you can choose this number 2% if, let's say, later on you can make some kind of amendments to get this number back to the level of significance which, let's say, is imposed on you by the regulator, okay? So you put in some multiplicative factor, you do whatever you want, but let's say I get it back to 99% confidence later on. The only reason I'm playing around with this alpha V is because I'm designing my VaR setup in such a way that backtesting becomes more powerful, okay? So in terms of actual capital setting, what I'll do is I will use some kind of a multiplicative factor. Both of them will use these factors. They will be different for both of them, but in the end they would get their numbers up to, let's say, 99% confidence, okay? So let's get back to these analysts A and B. So analyst A, because of the choices that he's making, he would end up with an expected number of exceptions, which is alpha V times T, which would be 10. And he would end up with a variance of these number of exceptions to be, just follow this formula, it would be 9.8, okay? On the other hand, what does analyst B end up with? He ends up with number of exceptions to be 30 and the variance of this number of exceptions to be 29.1. Okay, so this is where the two analysts stand. Now let's see which one of the two would be better positioned when it comes to the power of the backtest. So to understand that, what we can do is, let's plot the distributions of the two analysts, I mean the x's for the two analysts, and let's continue ahead with our backtesting. So let's do that. So what we have plotted here is basically distribution of X once we have done it for analyst A and then for analyst B. take a look at the numbers that we already know. We know that the expected value of number of exceptions for A is 10. So that's where, it's this graph, the blue graph is showing. And the orange graph or plot is showing us the expected value for analyst B as 30. The other thing which these plots are showing is that when we did follow our rules of thumb were increase alpha and increase the level or the length of the backtest window. We do find one more thing as well, and that is that the dispersion of the distribution of this X has increased. Okay, so this is about the two distributions. Now let's do this. Let's actually continue with our backtest. So let's continue first with analyst A. Analyst A would end up rejecting the null hypothesis, the hypothesis that the VaR model is a good model. If this condition is true, what he would do is he would compute a test statistic, and in computing this statistic, I am imposing the normality assumption. I am imposing this assumption that if I were to take the observed number of exceptions, subtract from it the mean number of exceptions, which is 10, divide by it or standardize it by the square root of the variance, which is 9.8, then I am assuming that this number is approximately normally distributed. So this guy, I mean the one in the absolute sign, is normally distributed, and I would end up rejecting the null hypothesis if my test statistic, the absolute value of it, turns out to be greater than 1.96. Here I am assuming that I am conducting this backtest at a 5% level of significance or 95% level of confidence. So it's a two-tailed test, and if I were to leave out a 2.5% area in each of the two tails, the cutoff value would be 1.96. Let's work out the cutoff value, I mean in terms of not the Z, which is the standard normal variable, but rather in terms of the X, which is number of exceptions. So open this up, what do you get? You would get, I would end up rejecting my null if X minus 10 upon square root of 9.8 is greater than 1.96, which solves to actually X is greater than something like 16.13. Same thing, when I apply it to the left tail, I can write it as X minus 10 upon 9.8 is less than minus 1.96. That means I am on the left of the left critical value. Okay, so this turns out to be an X, which is I reject my null if X is less than 3.86. Okay, now since this X is a discrete random variable, let's mark off the values on this distribution of X, which are my rejection regions. So when X is greater than equal to 17, then I would reject. So this is 20, 19, 18, this is 17, right? That means if I am on the right of this guy, including 17, I would reject my model, number one. Number two, if X is to the left of 3, I mean including 3, then I would reject my model. That means 0, 1, 2 or 3. So these number of exceptions, 0, 1, 2 or 3, they make me reject the VaR model. Okay, so these are my rejection regions. Now the probability under the area under this curve, which these rejection regions total to, is 5%. That's the way we've designed it, approximately 5. Okay, now let's do the same exercise for analyst B. So for analyst B, I would write down my rejection or accepting rule to be something like this. It would be X minus 30, that divided by square root of 29.1. This should be greater than 1.96. So therefore this boils down to I would reject my null if either X is greater than 41. I mean I have already included that discretization, the discrete bit. This should be including 41, or I would reject my null if X is to the left of 19. Okay, so let's mark off these two on this graph. So basically it would be this guy, right? If I am to the left of this guy, I would reject, or if I am to the right of this guy, I would reject, including both these, right? So where is analyst B placed relative to analyst A? See, analyst A could have ended up rejecting his model provided number of exceptions was, let's say, 0, 1, 2, or 3. And on this side, if it was 17, 18, 19, and so on. Okay. On the other hand, take a look at analyst B. The number of exceptions which you are giving him to sort of play around with is much more. Analyst B could have rejected the null if the number of exceptions was anything from 0, 1, 2, 3 right up till 19. Okay. So that ways, although both these graphs and the points at which we have sort of demarcated them, I mean in the tails, the rejection regions, their areas still boil down to 5%. I'm not saying that analyst B has a higher area. Okay. In terms of areas, they both mark off 5% in the tails, but analyst B has a longer rejection region, let's say in proportion to the total length of the backtest window, right? So analyst B, therefore, he has a bigger or a longer length on the x-axis which he can play around with. So therefore, there is a higher chance that if you were to give a bad model to analyst B, he would end up rejecting it. And that's what we are referring to as the power of a backtest. Okay. So therefore, just to recap about the rules of thumb, remember that if you would want to increase the power of a backtest, then please increase the level of significance, which amounts to decreasing the level of confidence at which you compute the VaR, and or try and increase or lengthen the backtest window. Okay. So if you were to do this, you would increase the power of your backtest.